Okay guys, so today we're continuing. If you have headphones in still or cell phones out and laptops, let's just put those away, please. Thank you. So we're going to continue with our trig identity stuff. We're going to do a few more examples today, and then the gift I'm giving you is the gift of time over the next few days to get prepped for our upcoming test. So time is important for trig identities. That's why we're doing 2 days of it. I rarely do this, as you guys probably have seen before, but I think it's important that we spend time practicing this, because the only way you get good at it is if you practice, like we said before. So just taking up our warm-up for today. We're going to make sure that we do this in proper form. So just to remind you, we separate out left side and right side. And we'll recopy what's on the left side of the equal sign and what's on the right side onto their respective sides here. Okay, tell me what you guys did to start this one. Nicole, yeah. I think you should for sure label left side and right side. If you don't put this horizontal line, it's not a huge deal. But so what was the first thing you guys did here? Essay? Sorry, can you speak a little bit louder? Turn what into a fraction? So what did you turn sine to? So 1 over sine x is cosecant x, right? I don't want to switch sine x to cosecant. Bonnie? Yeah, so we're going to leave sine. Sine is already in terms of sine, right? So the main goal that we talked about, the big golden rule, what was that big golden rule that we talked about? Liam? Change everything into sine and cosine. Yeah, perfect. So we have a tan here that we are going to change into sine x over cos x. And again, this comes from our little trig identity key here. We can see that tan is equal to sine x over cos x in this middle section here. So that's what I'm looking at. Okay. So the other suggestion was that we start working with the more complex side, and we kind of try to simplify that. So where did you guys go from here? Alex, where did you go? Okay, so what did you get? Great. So we want to think of this as if it's sine x over 1, right? So when we multiply this, the sine x gets multiplied into the numerator, and the denominator is just being multiplied by 1. Okay, and then the other tip that I gave you guys was we try to always merge those two fractions. So they already have a common denominator, which is nice, so we can actually just put them into one fraction here. And we're so close right now. What are the last few steps here? Kendall?
The numerator can change into cos squared x.
That's right. And cos squared x divided by cos, we can cancel 1 out from each, and we're just left with a cos x on top. Okay, so this guy right here, going from 1 minus sine squared x, I asked you guys to add this onto your sheet, but that comes from the rearranged version of this Pythagorean identity. And this Pythagorean identity says I can move either one of these two things to the opposite side. So cos squared x, if I move the sine squared x to the other side, is 1 minus sine squared x. And then I can do the reverse as well. So make sure you have that added, because we do use these ones a lot. Okay, so that's where I got 1 minus sine squared x is equal to cos squared x. And then we're going to end this out with left side equals right side and square. Okay, all right, I want to go over a couple extra little things that you might approach in working with some of your questions. The first thing is something like this: sine x plus cos x squared. Now, the biggest mistake, even some of my grade 12s still do this, they have x plus y squared, and they let that equal x squared plus y squared. So is this equal to sine squared plus cos squared? Am I allowed to just distribute this squared inside here to each thing? No, this actually is not equal to sine squared plus cos squared. How do I figure out what this is equal to? What does something squared mean? Joey? Yeah, so it's that thing times itself, right? So it would be sine x plus cos x times sine x plus cos x, and then what we have to do is first, outside, inside, last. So we do sine x times sine x, that would give us sine squared x. And then I would do sine x times cos x, which would give us sine x cos x. And then I would do cos x times sine x, and I usually keep these consistent, so if I wrote one as sine x cos x, I'm not going to write the second one as cos x sine x, I'll just write it as sine x cos x, because it's like 7 times 2 or 2 times 7, same thing. So I'm going to write this again as sine x cos x, just so that we can see that those are actually a similar term there. And then last, cos times cos is cos squared. Okay, simplifying out here a little bit, you have 2 sine x cos x's. And you will also notice here that if I rearrange a little bit, I think you have to do this in a couple of your questions on your worksheet. What is this equal to? This equals 1. This is a Pythagorean identity. So when I expand that thing out, I have to look and see, of course, where I'm headed if I'm using this in a question, but this could be an extra little step that you use to simplify a little bit here. I think you need this in number 15 on your sheet, if I'm not mistaken, and I think it's also in another question as well on the, from questions 2 to 13 on that left side. Okay, so this is an important skill. Make sure you FOIL properly. Another skill that I want to just introduce to you guys is this kind of idea. So we kind of do exponent laws in reverse, in a sense, with this little rule. And I'll show you the usual way that you guys know of, and not with trig to start. So if I had an exponent of an exponent, let's zoom in here a little bit. If I had an exponent of an exponent, how would I simplify these? Bonnie? We would multiply the 2 exponents. So I should be able to either go forward with this, and if I have an squared to some exponent 3, I can multiply them. But I should also be able to bring those back out into their own individual kind of pieces as well. So if I have, you might notice that you end up with something like sine to the exponent 6. I don't have very many sine to the exponent 6's that I can simplify. But I do know what sine squared is equal to. I know sine squared, I could maybe use 1 minus cos squared or something like that. So usually if I see something that's greater than an exponent of 2, I will try to simplify that thing using my exponent laws. So I'll express that as like sine squared cubed, kind of like how we're going from x squared cubed to x to the exponent 6. I'm doing the reverse when I express sine to the exponent 6 is equal to sine squared cubed. So does everybody see how that works? So if I multiply these guys back, I'll get the 6 back. So we're going to make sure we use exponent rules to our advantage here. Okay, so just be aware that we can do that. Nicole? I'm going to give you an example in one of our examples today. Yep. Never fear, Nicole. I got you. Okay, so those are just a couple little extra things that we should know. So remember, we have our tips from the first lesson. If you ever get stuck as you're proving, always look back to those tips. And see if they can help you. And we'll add these kind of like to our tips list as well. Okay, so we're going to try a couple different examples today and see what we can do with these. And then you guys will have some time to practice on your own. So we're going to set up our left side and right side. And just rewrite the left side and rewrite the right side as usual. So it's important for you guys to know that just because I do a certain solution doesn't mean that there aren't other routes to kind of get to the same answer. So sometimes you guys might even see that I start a proof in some of the solutions and then I scribble it out and I start again because my method just wasn't working. So sometimes it happens that you try a method and it just doesn't work, and then you go back and you start again and you try a different method, right? You try different approaches and you kind of see what works to do these proofs. So even with my practicing and my experience, sometimes I approach something the wrong way and then I have to try something else. And that's okay, okay? So don't get discouraged when you're doing these. Also, if you happen to do a different proof than I did, that's totally okay, as long as your proof holds up and like all of the math that you did is correct. But there are multiple different routes that we can take to get to the same answer. So in this question here, there's actually a couple of different routes that we could take. We could do the typical change everything in terms of sine and cosine. That is a possibility. I could also potentially use like a Pythagorean identity because I know that tan squared x is actually equal to secant squared minus 1 if I look at my sheet here. So looking at my Pythagorean identity here, I know tan squared x, if I move this 1 to the other side, is equal to secant squared minus 1. So I could potentially try that. I could try replacing my tan squareds with sine squared over cos squared. What do you guys want to try? Do you want to, Ideas, Joey? You want to try the Pythagorean identity? Okay, so let's try that out. I'm not going to change sign just yet, but let's see what happens if we kind of place this in here. I'm using a Pythagorean identity. And I'm still going to kind of try to turn everything, now that I've used that identity, I want to think of secant squared x as if it is its reciprocal identity, which is 1 over cos squared. So you'll kind of notice here that if I distribute this guy in, I'll get secant squared x times sine squared x minus sine squared x. So just distributing that sine squared x in and multiplying it by each term. And then if I think of secant squared x as its reciprocal function, cos squared x, you guys might start to notice something about how we are almost getting to the left side here. Joey?
Why did you sine squared x?
Because I distributed it into each term in the bracket here. So when I multiply this sine squared up here, what do I actually have? I have sine squared x over cos squared x. What is that equal to? Yeah, it's equal to tan squared x. Okay, so I still, even though I didn't necessarily turn everything right away into terms of sine and cosine, I was still able to get to the right answer here. So I just kind of wanted to show you guys a bit of a different approach here. Part of why I kind of like this approach is because as soon as I plug in this secant squared x minus 1, I now have this minus here that I have over on the left side. So see how the left side has 2 terms and the right side doesn't have like any subtractions or anything like that? By using this identity right here, I put that subtraction in. So I'm kind of looking at where I'm headed to see how I can do this. Now, could you have replaced your 2 tan squared x's with sine squared x over cos squared x and then worked on the left side to find a common denominator and merge? Absolutely. But I think that this approach was actually probably the more efficient approach. But again, it doesn't matter. You can always get to the same answer. Okay, so we'll end this guy out with left side equals right side. Oh, I'm frozen here for some reason. Oh, there we go. So left side equals right side, and box. Any questions on this one? Joey?
How did you get sex squared into the reciprocal square?
So this is a reciprocal identity. So if you look at your sheet here, secant is equal to 1 over cos. So we were kind of talking about in our tips and tricks from the first lesson that if I like square this side and square this side, the equation still holds true. So it's like secant squared equals 1 squared, which is 1 over cos squared. Any other questions for this one? Okay, let's try another one. Okay. So we don't have any squareds or anything like that in here, so I think we won't really be able to use those Pythagorean identities like we did in our first example. So I think our best route, again, like I said, 95% of the time this will be the best route. Let's turn everything in terms of sine and cosine and then just see what we can simplify. So secant x is actually equal to 1 over cos x. And I can't really do much more with that right side. So my goal is to make the left side equal to 1 over cos x, if I can figure that out. I'm also going to replace tan x with its sin x over cos x identity. That's in the middle top there. And now I have two fractions. What do I do with fractions when they're being added or subtracted? Common denominator. Okay, so each side needs what the other side has. So this side needs a cos x on top and bottom. And the left side here needs a 1 plus sin x on top and bottom. Okay, so just putting these guys together here. And I'm going to write them all under one denominator. So it'll be like 1 plus sin x times cos x. Okay, major rule here, this is an alert. We don't want to start doing this and canceling out. Sorry, that might be hard to see. We don't want to start doing this and canceling out like this. Why do I not want to do that? There's an addition sign, exactly. So no canceling separate pieces at this point. I need all multiplication. This is a problem right here, so no canceling separate pieces. Please, please, please. What we can do is we can expand the top and see what we can simplify. So I'm going to bring that sine x in there, and I'm going to multiply these two cosines, and we'll see what we get on top and what we can do from there. So 1 times sine x is just sine x. Sine x times sine x is sine squared x. And cos x times cos x is cos squared x. The bottom I'm going to leave. It's already fully factored. So I don't think we need to expand that one. And I don't know that it's really going to help us to expand it either. Okay, so look at where we're headed. Where we're headed, I need a 1 over cos x. I have the cos x part of that, right? Look at, I have that cos x on the bottom. And that should probably be this cos x right here. So are there any ideas as to how we might simplify the top a little bit to kind of get us to this last part here where we need that 1? Alex? We can do that, but you're doing 2 steps when you only need to do 1. Katie?
Sine squared x plus cos squared x equals 1.
Yeah, this already equals 1. Okay, that's a Pythagorean identity. If you plug in cos squared x is equal to 1 minus sine squared x, then you'll get to 1 in a roundabout way, but you'll do 2 steps instead of 1. So here we go. We've got sine x plus 1 now over 1 plus sine x times cos x. Thoughts from here? Yeah. So do you guys agree that 1 plus sine x is the same thing as sine x plus 1? Is 3 plus 1 the same thing as 1 plus 3? Yeah, it is. So we can cancel those out. What's left on top? A 1 is left on top. Good. So now we have, now we have 1 over cos x. And we have left side equals right side. Okay, any questions on this? Nicole?
How do you know when writing the addition sign is a part of the term or separate?
So in this case right here, if I had like a full grouping of this in the denominator, I could cancel it all out with the denominator. But again, I'm still not canceling up here. I'm not canceling separate terms. Like I'm not canceling just the sin x. I'm canceling the whole group with another whole group.
Like,
Is that what you're asking me?
like with the sin x plus 1.
Yeah.
Because that's one whole group.
Yeah.
Let's say with sin x plus 1 plus...
Then I would not be canceling out the sin x plus 1. It needs to be the whole group or nothing, right, when you have an addition sign. If it was sin x times something else, like let's say it was like times tan x, then yeah, I can do that. But as soon as I have like the addition or subtraction of like another term, let's say it was like plus cos x, I can't cancel that single part out.
But let's say you have like 1 plus sin x in brackets at the top, and then times like 2 plus sin x.
Yeah,
That's okay.
yeah. Yep, because it's all being multiplied. And I have to cancel out like that full group, right? It has to be the 1 plus sin x, the full group gets canceled out with another full group in the denominator. Can't just be like a piece of it, right? Yeah. Okay. Last one, and then you guys are going to do some practice. Okay, this little symbol right here is called alpha. Again, if you feel happy about changing that to, that would be left side. If you feel happy about changing that to x and you feel better about that, that's fine. You can go ahead and do that. I did a bad alpha there. Okay. So you guys see why I told you that last little tip there, right? Because now we have a sign to the exponent 6. There's two ways that we can do this. We can work on the left side and we can use our exponent laws, or we can work on the right side and try to simplify this to get to sign to the exponent 6x. So I'm going to show you the way in which we do exponent laws in reverse, but you could choose either side to start working with here. Both ways should work. But sign to the 6, I told you guys whenever I see that, I try to express that as like sine squared cubed. And then what do you guys notice here? We're almost there to make these two guys equal. What do we need to do, Katie?
You change sine squared cubed to 1 minus cos squared x.
Great. So this is a rearranged Pythagorean identity here. So sine squared we know is equal to 1 minus cos squared. So I'm just using that. I could have also, again, I could have worked on this side and I could have made this sine squared, and then I could do squared cubed, which gives us sine to the 6. So again, a couple different ways to get to the same place. Okay, and now we'll just say left side equals right side with our little box. Okay, so this is exponent rules here. Again, you guys don't have to put those little notations. I just put those just so you guys know when you're looking at your lesson. Questions for this one? We're all good? That one was a pretty quick one.